I don't know the question number. I think it's 18. Yeah, it's 18. I'm doing fluid mechanics. Actually revising. And I'm revising the good questions. So question is there is a solid cube and it's put in mercury with one-fifth of the height. One-fifth of the height is inside this mercury. So this is I think I've made it from the wrong perspective. So it's like the part submerged look maybe like this. Be able to see it clearly. Let me so it's something like this. With the cube in mercury. So mercury is silvery, but I've made it yellow. Anyways, with one-fifth of the height inside, one-fifth of the height inside this mercury, it's an equilibrium. Now the question is, if this is a container and we're pouring over water, till what height should we pour the water so that it's like almost underneath the whole cube is almost underneath the only the surface is on the top. It's not 4 by 5 of the height because when we pour water it will give some buoyant force. For equilibrium the heights will change. So yeah, let's start. So 1 by fifth of height means if we calculate the volume, height times area, and normal volume is height into area. So the volume is 1/5 too, and it's an equilibrium. Since it's an equilibrium, so V and rho of metal, which is not given, G is equal to volume of water displaced. So my fifth, actually it's not water, sorry, it's mercury. Mercury G. And so the density of metal is 1 by fifth of the density. Wait a second. Uh, ah. So the density of metal is 1 by fifth the density of mercury. And nothing wrong since mercury is very dense metal. Now, uh, so we got this and then we are pouring over water. It's no longer 1 by fifth. But it's the whole height. And let's assume the height underwater is h, and this is, of course, the edge minus h. So inside the mercury. Actually, the diagram is a bit wrong from the perspective. Should be something like this. Anyways, so you have equilibrium. So come on, it's volume. The whole volume is inside. Volume and density of metal G into the volume inside, which is H. In water, it's A is the cross-sectional area. Then it's volume of density of water G plus inside this mercury is H minus H into area of cross section density of mercury is of metal G. We cut it, and now we have the volume and the whole. This volume can be written as the height, the whole height is the edge, the cross sectional area. This A gets cut. So the edge times rho of metal. Given the rho of mercury, so I have to convert it to in terms of density in mercury. This is 1 by 5th of mercury. Rho of mercury 1 by 5th equal to height. We do not know. So let's light the values. Let's not take much time. So the edge is given is 12 into 10 to the power minus 2 if I'm not wrong. Of metal is 1 by 5th of mercury. Mercury is given 13.6 into 10 power 3, but that power will get cut. So 10 power 3 will get cut. So it's h into 10 to the power 3 that will get cut. So it's just h plus, then use the distributive property. And mercury, we know that it's 13.6 minus h 13.6. Now we just multiply 5h. This is 5 times 12 is 60. And with 13.6 is 68. All right. Now this 5 minus 68h comes out to be 63 minus 63. It comes over here, so it becomes plus 63h. Then we calculate this thing. You can basically take 10 minus 2 and this 60. And take 10 minus 2 into 13.6 common. It come out to be 10 minus 2 into 13.6. 48. 48 times 13.6. So that's what is it? So 48 at 0, 24, 28. That's only 4, 14, half another 4, 5, 8, 2, 5, 6, 6, 5, 2.8 upon 63 is h, written power minus 2, of course. Let's convert, if we convert it to centimeters, then the 10 power minus 2 is gone. Yeah, this is the answer in centimeters. So about approximately 11 centimeters. That's it. Or 10. It's like more close to 10 than 11. But I'll rather say it's 10. It's 11. Okay. That was it.